In this video, we're going to talk about counting, section 4.4, that will wrap up chapter 4. And in this video, we're going to talk about how to develop the ability to apply the fundamental counting rule, factorial rule, permutations rule, and combinations rule. Also, we'll distinguish between circumstances requiring the permutations rule and those requiring the combinations rule. Okay, so here probability problems typically require that we know the total number of simple events, but finding that number often requires one of the 5 rules presented in this section. Here, this section requires greater use of formulas as we consider different methods for counting the number of possible outcomes in a variety of different situations. So here we're going to be looking at 5 different counting rules that can be used, starting with the multiplication rule. That's rule number 1. And we call this the multiplication counting rule. And it is used to find the total number of possibilities from some sequence of events. So if we have a sequence of events in which the first event can occur in 1 ways, the second event can occur in 2 ways, the third event can occur in 3 ways, and so on, then the total number of outcomes is going to be n1 times n2 times n3 times, and so on. We just simply multiply all of those possibilities there. So in example number 1, let's say here the thief steals an ATM card and must randomly guess the correct 4-digit PIN code from a 9-key keypad. Repetition of digits is allowed. What is the probability of a correct guess on the first try? All right, in this case here, there are 9 keys on the keypad, so we do allow repetition. So for that 4-digit PIN code, the first digit can be selected 9 ways. The second digit can be selected also 9 ways. The third, 9 ways. And the fourth, 9 ways. So this is just simply 9 times 9 times 9 times 9. So if I enter it like this, or I can say 9 to the 4th power, since 9 is used as a factor 4 times, this will end up being 6,561. So there's 6,561 ways for a 4-digit PIN code, but only one of them is correct. So the probability of getting a correct 4-digit PIN code that's going to be this as a fraction. So only going to be one way to do it out of 6,561. And that will just be the fraction itself. Okay, here's another example of that, of the multiplication counting rule. A social security number consists of 9 digits in a particular order, and repetition of digits is allowed after seeing the last 4 digits printed on a receipt. If you randomly select the other digits, what is the probability of getting the correct social security number of the person who was given the receipt? Okay, so only the last 4 digits of that social security number is known. The other 5 are unknown. Okay, and you only have digits from 0 to 9. So it's 10 digits to choose from. So for the first number in the social security number, there are 10 ways. The second, 10 ways, the third, 10 ways, the fourth, 10 ways, and the fifth, 10 ways. Okay. We already know the last 4 digits of that person's social security number. Okay. To find the others, we have to multiply 10 times 10 times 10 times 10 times 10, or 100,000, because this is like 10 to the fifth. So 10 to the fifth is 100,000. Okay, so there's 100,000 ways of getting the social security number if we already know the last 4 digits of that social security number. But there's only one correct social security number there. So the probability for someone to come up with a correct social security number after knowing the last 4 digits, that's going to be that one way out of 100,000. And we'll again leave that as a fraction. So that's going to be your probability of getting the correct social security number. All right, now let's look at rule number 2, the factorial rule. The factorial rule is used to find the total number of ways that n different items can be rearranged, and in this case, the order of the items matter. The factorial rule uses the following notation. We use the factorial symbol, which is the exclamation mark. That denotes the product of decreasing positive whole numbers. For example, if we have 4 factorial, that would be equivalent to saying 4 times 3 times 2 times 1. And if we multiply that out, you'll get 24. And by special definition, 0 factorial is automatically going to be 1. Okay. And the number of different arrangements of n different items when all n of them are selected is n factorial. And again, order does matter. Okay. So if we look at example 3, it says here, if you know the names of the remaining 4 students in a spelling bee, what is the probability of randomly selecting an order and getting the order that is used in the spelling bee? Okay, so we know the names of the remaining 4 students. Okay, selecting an order, that means that order does matter, so we have to use the factorial rule here. So it'd be 4 factorial. And to find 4 factorial, we just take the product of decreasing positive whole numbers. So we start with the 4, then it'll be times 3, times 2, times 1. And if we multiply those numbers, 4 times 3 times 2 times 1, you will end up with 24. So 4 factorial is equal to 24. Now they want the probability of randomly selecting an order and getting the order that is used in the spelling bee. So the probability of getting the order that's used in the spelling bee. And there's only one way for that to happen. So it'll be 1 over 24. And we're going to leave that as a simplified fraction. Okay. Here's another example of the factorial rule. A moving company has a truck filled for deliveries to 9 different states. If the order of the deliveries is randomly selected, what is the probability that it is the shortest route. All right, so this moving truck is going to 9 different states. It's not going to go to the same state again. So this will have to be a factorial rule that we have to use here, non-factorial. And of course, non-factorial would be this if we were to write this out. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, if you were to multiply this out using your calculator, you would get 362,880. Now, you can use your TI-84 calculator to get non-factorial. To do that, all you have to do is press the number 9. Now, there's a button that says Math on the left-hand side. You'll press that button. You're going to use your right arrow key to go over to this menu item that says PROB, meaning probability. And you'll see these choices. The one you want to select is number 4 because it has the exclamation mark or the factorial symbol. Okay, you can go down, use your down arrow key to highlight number 4 and press enter. And then you'll see on the screen non-factorial. Press enter. You'll get the 362,880. Now, we want the probability that it is the shortest route. So there's only one way of doing that. So the probability of the shortest route and it's equal to 1 over the 362,880. Now again, we'll leave this as a simplified fraction. All right, on the next page deals with permutations and combinations. And we'll be answering the question, does order count? Now, when using different counting methods, it is essential to know whether different arrangements of the same items are counted only once or are counted separately. The term permutations and combinations are standard in context, and they are defined as follows. So here we got a couple of definitions to deal with here. Permutations of items are arrangements in which different sequences of the same items are counted separately. That is, the order is of importance. Okay, so here we're dealing with the order, so that means we need to deal with permutations here. On the other hand, combinations, those are arrangements in which different sequences of the same items are not counted separately. In other words, the order is not going to be of importance when you're dealing with combinations. Okay. And you might want to think of something like this: permutation position. So here, with permutations, that may help you think that permutations, in this case, the position does make a difference. And then the other one is combinations committee. That may help you remind you of members of a committee where the rearrangements of the same members result in the same committee. So the order will not count. Okay. All right. So let's look at number 3, the permutations rule. And this is for where all of the items are different. Okay. And the notation for that would be N with a capital P and then lowercase r. That's how we write the permutation of N choose R. And the formula for that would be this: n factorial divided by the quantity n minus r factorial. And that's going to be the number of different permutations where the order counts when n different ways are available, but only r of them are selected without replacement. Okay. And we did talk about without replacement in one of the other videos here when we were dealing with the addition and the multiplication rule. Rearrangements of the same items are counted being different. For example, if 5 letters A, B, C, D, and E are available, and 3 of them are to be selected without replacement, the number of different permutations is as follows. So here we got NPR, that's going to be n factorial divided by the quantity n minus r factorial. Here your n is going to be 5. Okay. That's the number of items that are available that we have. R is the number that's available to be selected without replacement. So in this case, the R is going to be 3. N will be 5. So it'll be 5 factorial divided by 5 minus 3 factorial. Okay. And if you simplify this out, it would be equal to 60. All right. Now let's take a look at example 5 here. A presidential candidate plans to begin her campaign by visiting the capitals in 3 of 42 states. What is the probability that she selects the route of 3 specific capitals? Okay, so in this case here, she's visiting 3 capitals of 42 states. That's your N. N is 42. And she's choosing 3. So R will be 3. Now she selects the route of 3 specific capitals. What would be the probability of that happening? All right, this is actually a permutations problem here because this is going to be done without replacement, meaning she's not going to visit that same capital again. So the way we write this will be 42 with a capital P and then 3. NPR. Now that's going to be equal to n factorial, that's the n, which is 42, factorial, divided by the quantity of n minus r factorial. N is, again, 42 minus r, which is 3. And that difference is going to be factorial. So when I simplify this, I have 42 factorial on top. On the bottom, 42 minus 3 would be 39. So the denominator is 39 factorial. Now here's where I use the product of decreasing positive numbers here. I'm going to write 42 factorial as this: 42 times 41 times 40 times 39. And I'm going to stop at 39. So I'll stop at 39 factorial because if you notice in the denominator, I do have 39 factorial. So when I simplify this, the 39 factorials divide out. So all I'll be left with is multiplying 42 times 41 times 40. And this will give me 68,880. 68,880. So that's like 68,880 ways of visiting visiting 3 capitals in 42 states. Now we can do this in the calculator as well. That 42P3, we can do that by typing in the number 42 first. and then press the math key. Use your right arrow key to go to PROB for probability. Notice under menu item number 2, you see NPR. That's why I typed in the 42 first, because if I'm going to use that, I need to type the number that's on the left first. So I'm going to go ahead and select number 2 for NPR. Now notice on this calculator, you'll see the 42 on the left with the P there, and then a small box. That's where I need to enter the number that's on the right, which is the 3. And you'll see I come up with 68,880. Okay. Now, they want the probability that she selects the route of 3 specific capitals. There's only one way for that to happen. So the probability of selecting a route of 3 specific capitals is equal to, there's only one way to do it, out of 68,880. Okay. And we're going to leave that as a simplified fraction. Okay. Here's another example. With a short time remaining in the day, a delivery driver has time to make deliveries at 6 locations among the 9 locations remaining. How many different routes are possible? This too is a permutation problem, because he's not going to make a delivery to that same location again. So it'd be 9P6. And by the way, the keyword here is different. How many different routes? So that means he's not going to go back to that same route again. Okay. So if I do this by hand, it will be this. The n factorial is the number on the left side. That'd be 9 factorial divided by the difference of n minus r, 9 minus 6. And that difference is going to be factorial as well. Okay, if I do 9 minus 6 in the parentheses, I'm going to get 3. So this will be 9 factorial divided by 9 minus 6, which is 3 factorial. Now, if I was to write this out completely, then 9 factorial will be 9 times 8 times 7 times 6 times 5 times 4 times 3 factorial. I stop at 3 factorial because the denominator is 3 factorial. And notice that these 3 factorials divide out. And that will leave me with 9 times 8 times 7 times 6 times 5 times 4. Multiply all that out, you'll get 60,480. Now, the only question just says how many different routes are possible. So we ended at 60,480. That would be the number of possible different routes for this delivery driver. And again, you can do this in the calculator by typing in, for 9P6, I type in the number 9 first and then press the math key. Right arrow to PROB, and then select menu item number 2, which is NPR, press enter. And then type in the number 6 and then press enter. You'll see that it's 60,480, which is what I came up with. Okay. Rule number 4 is going to be another permutations rule, but this time it's going to be when some items are identical to others. Okay, and this is what we use for permutations: n factorial divided by n1 factorial times n2 factorial, and so on, all the way up to n sub k factorial. That represents a number of different permutations. Again, the order counts when n items are available and all n are selected without replacement, but some of the items are identical to each other's. Like n1 are alike, n2 are alike, all the way up to n sub k are alike. Example of that would be this. If 10 letters, where we have A, B, B, C, C, D, E, are available in all 10 numbers, or in all 10 of them are to be selected without replacement, then the number of different permutations will be as follows. And this will be it. The numerator in factorial, there are 10 numbers, so that's 10 factorial. Notice that these 4 A's are alike. So that's 4 factorial. I have 2 B's, they're alike, 2 factorial, and 2 C's, another 2 factorial. The D and the E appear only once. So 10 factorial will be 3,628,880 divided by 4 factorial, that's 24. 2 factorial is 2. 2 factorial is 2. Simplify this, you'll get 37,800. Okay. All right, take a look at example 7. A classic counting problem is to determine the number of different ways that the letters of balloon can be arranged. Find that number. So here we have the word balloon. And we want to find the number of different ways that the letters in that word balloon can be arranged. All right, so now the numerator is going to be the number of letters in balloon. That will be factorial. So there's 7 letters in the word balloon. That's 7 factorial. The denominator is going to be this. I see 2 L's in this word balloon, 2 factorial, and 2 O's in balloon, another 2 factorial. The B occurs once, the A occurs once, and the N occurs only once. Okay, so if I figure this out, let's see, 7 factorial, I'm going to write this out as 7 times 6 times 5 times 4 times 3 times 2, and I'm going to say 2 factorial. Because in the denominator, I have a 2 factorial. I bring down this 2 factorial and expand 2 factorial as 2 times 1. And then I'll divide out wherever I can. I know I can divide out the 2 factorials. Let's see, 2 times 1 is 2. So this 2 can go into this 4 2 times. So notice what I have in the numerator, just a 7 times 6 times 5 times 2 times 3. Multiply that out, you get 1,260. Okay, so there are 1,260 ways, or 1,260 different ways that the letters in the word balloon can be arranged. Okay. Here's another example. How many different ways can the letters of leggings be arranged? Okay. That's another one of those permutations rules where you have the same items being identical to others. Let's count the number of letters in leggings. There's 4, there's 8. 8 letters in the word leggings. Their numerator will be 8 factorial divided by, there's only 3 G's in leggings. So that's going to be in the denominator 3 factorial. The L occurs once, the E occurs once, the I occurs once, the N occurs once, and the S occurs once. So it's 8 factorial divided by 3 factorial. Let's say if I expand this out, this will be 8 times 7 times 6 times 5 times 4 times 3 factorial. That will be divided by 3 factorial. Here the 3 factorials divide out. So all I have to do there is just 8 times 7 times 6 times 5 times 4. And that would give me 6,720. So here there are 6,720 ways that the letters in the word leggings can be arranged. Okay. All right, now for the 5th and final rule, we're going to be dealing with combinations. This time it's going to be NCR. And that's going to be equivalent to n factorial divided by the quantity n minus r factorial multiplied by r factorial. This represents a number of different combinations where the order does not matter when n different items are available, but only when r of them are selected without replacement. Okay, and note that rearrangements of the same items are counted as being the same. So for example, if the 5 letters A, B, C, D, and E are available, and 3 of them are to be selected without replacement, the number of different combinations will be as follows. So here, NCR is this formula here. Your N, there are 5 letters, only 3 of them are selected. We're choosing R, choosing 3. So R is 3. 5 factorial divided by the quantity 5 minus 3 factorial times 3 factorial. 5 factorial is 120. Now 5 minus 3 will be 2, but 2 factorial will be 2. 3 factorial will be 6. 120 divided by 12 will be 10. Okay. All right, so let's look at this example here, example 9. When testing for current in a cable with 11 color-coded wires, the author used a meter to test 4 wires at a time. How many different tests are required for every possible pairing of 4 wires? In this case here, this is a combinations problem because here the order is not going to matter. In this case, the order that we choose, those color-coded wires are not going to matter. So we got, let's see, we got 11 coded wires. So the 11 needs to go here, and then C, and every possible pairing of 4 wires. We're choosing 4. You want to put the largest number on the left side and the smallest number on the right side. Otherwise, your answer will not make sense. So in this case here, your N is 11. So the numerator will be 11 factorial divided by N minus R, 11 minus 4. Factorial. That'd be multiplied by the R in this case, which is 4 factorial. Now let's simplify. 11 minus 4 is 7. So that means I'm going to have 11 factorial on top. That's divided by 11 minus 4, that's 7 factorial times 4 factorial. Now, if I expanded this out, the 11 factorial will expand as 11 times 10 times 9 times 8 times, and I'll stop at 7 factorial because the denominator does have the 7 factorial there. Now that 4 factorial, I'll expand that as 4 times 3 times 2 times 1. Okay. Let's divide some numbers out. 7 factorial, that's gone. I know 4 times 3 times 2 times 1, if I multiply that out, that's 24. And 9 times 8, that will be 72. I know 24 goes into 72 3 times. So now in the numerator, I have 11 times 10 times 3. And I'll end up with 330. Okay. So in this case, 330 different tests are required for every possible pairing of 4 wires from the 11 coded wires. Now, again, if we want to use the calculator, we do have the combinations. We have combinations on our graphing calculator here. So here we start by typing in the number 11 and then press the math key. Then go over to PRB. This time is menu item number 3 in CR. Hit enter. Hold on. Okay. There we go. And then select it, type in number 4. That'd be 330. Okay. There is one more problem, one more example of this. All right, in a small private school, 6 students are randomly selected from 19 available students. What is the probability that they are the 6 youngest students? Okay, order does not matter. So we're going to be dealing with the combination problem here. So there are 19 students, we're choosing 6. So it'll be 19C6. Again, the largest number has to be on the left side, the smallest has to be on the right side. Otherwise, when you do that combinations formula, you're going to get a negative number in the denominator. That does not make sense. Factorials does not work for negative numbers. So using the formula, the numerator is your n, that's 19 factorial, divided by n minus r. N is 19, r is 6. So it'll be 19 minus 6 factorial times r factorial, which is 6 factorial again. Now simplify the parentheses. 19 minus 6 is 13. So I'm going to have 19 factorial divided by 19 minus 6, which will be 13 factorial times 6 factorial. Let's expand 19 factorial out as this. 19 times 18 times 17 times 16 times 15 times 14 times, I'll stop at 13 because I got 13 factorial in the denominator. And then that's going to be multiplied by, let's see, 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. And now let's see if we can divide some numbers out. 13 factorial is gone right off the top. Let's see. I know this 6 goes into this 18 3 times. I know 5 goes into this 15 3 times. Let's see, 4 goes into 16 4 times. Get me out here. I'm going to say here, 1 time, well, let's do this. 1 times 2, that's 2. That goes into this 14 7 times. Oh, and this 3 right here can go into this 3 right here 1 time. So all I'll be left with is this. I'm going to write this out. 19 times 3 times 17 times 4 times 7. So in this case, if I do 19 times 3 times 17 times 4 times 7, I'm going to get 27,132. That represents the number of ways of selecting 6 children, 6 students. But it says it was the probability that they are the 6 youngest students. There's only one way for that to happen, for you to get the 6 youngest students. So the probability of getting 6 youngest students will be 1 over the 27,132. All right. So what I talked about in this section, I've already presented the 5 different counting rules. Now, not all counting rules can be solved with these 5 rules that I mentioned, but they do provide a strong foundation for the most common rules that can be used in a wide variety of real applications. Okay. All right, so that will complete this video on section 4.4 that deals with counting. The homework is available. I mean, whenever it's open, please try to work on that. Follow this video as much as you need to, and do feel free to email me if you have any questions about any of the homework for this section.